Hello, this short episode is about the relation between the roots of a polynomial and its coefficients. This relation is known as Vietta formulas. And in writing this relation we will encounter something just called elementary symmetric polynomials. And the plan is also to mention the special role played by those elementary symmetric polynomials. So let's start with a polynomial in one variable t. Let's assume that it is monic, which means that the leading coefficient, the coefficient for the highest term degree, d, is 1. So that means that when we factor it into a product of linear terms, the number of factors will of course be the same as the degree, but we don't need to put any coefficient in front of the product. That is of course possible, say, over complex numbers when we use complex coefficients, but in general just let's assume that our polynomial is with arbitrary coefficients from an arbitrary field. It is possible to factor into the product of linear terms. What can we say about this root if we know the coefficients? So again, being monic means that the leading coefficient is said to be 1. Well, that is a matter of simple algebra, so if we want to match these two sides, we just need to rewrite the product as a sum, and that is basically to see what is the coefficient for the power of t in this expression. Say for the first power, we can obtain it in a sum by taking t from one of the factors and taking roots from all the others, and in this expansion, in the process of expanding this first coefficient, we will have the sum of all the roots. All of them will have to be taken. So that is not the first, that is d minus 1, that is first after the leading. The sum of all the roots with minus coefficient. So what I said incorrectly. I'm building the coefficient for the next after the leading power. So I'm to take d minus 1 copies of t from almost all factors but 1, and from that 1 I have to take the other coefficient negative root, and then when I go through all such products I will see this coefficient coming. So then the other extreme, when we go all the way down to the free term and look at the free term, and that means that we don't have t's at all. That means that in all these products we have to choose the free coefficient, the root, and then take the product of all of them. So the answer will be easy product of all the roots, but they will come each with minus sign, so the overall minus sign contribution will be to the number of those roots. So let's also record what happens in between. So step j, when we look at the t to the power j, and that means that we take t from j factors, and from the rest we have to take the roots. So maybe I will be better off if I'll just say that this is not j but d minus j. And then I will have to take d minus j t's, so from d minus j factors I'll have to take t, from the rest I'll have to take the root, so I'll have to take j root. The number of minuses will be minus 1 to this number j, and then I will be taking some roots, and since I'm going to form a product of them, j such roots, they will have to be all different. I'm taking them from different factors, And since I'm forming products out of them, it doesn't matter. It can be made, this product can be made such that the first index is less than the second, and so on. So I can order my roots in the product, each product, in such a way that the first written is, its label is less than the second, and so on, all the way down to the last jth. So that is a generic form of a coefficient. These formulas are called Vietta, formulas after François Vietta. For example, if t is equal to, say, 3, then our monic polynomial will look like t cubed plus some coefficient, say, f2t squared plus f1t plus f0. So that is a generic form of a monic polynomial, and then let's assume that c1, c2 and c3 are its roots. So then what we can say about f2 is that it is negative the sum of c1, c2, c3. f3 is, sorry, f0 is the product, again with negative sign, of c1, c2, c3, and the coefficient in between, f1, is positive sum of products of two, c1, c2, c1, c3, c2, c3. And in general, that is a feature of Vietta's formulas, that the sign changes if you progress along the list of your coefficients. So you start, for the subleading term, you start with minus, and then you go plus, and then you go minus, and so on, all the way through. And these expressions of coefficients as roots, these terms, expressions in terms of roots, are symmetric in these roots, and that is, of course, inevitable, because roots are all on equal footing. There is no root number 1 and root number 2. It's our choice. It's an artificial numbering of them, so they're all on equal footing. All the expressions containing them have to be symmetric. So elementary symmetric polynomials are those expressions. Sigma 1 in x1 up to xd will be just the sum of these unknowns. Sigma d, the very last on that collection of variables, will be the product of all of them. And all the way through in between, so say sigma j of x1 xd is the sum of all possible products of j copies of the variables, but all the variables will have to be different. And that is assured by this ordering, and each such product is appearing once. So these are elementary symmetric polynomials. What is so special about them? This is the main theorem on elementary symmetric on symmetric polynomials. That any symmetric polynomial in these variables x1 up to xd is in its own right a polynomial called polynomial expression of these elementary symmetric polynomials. Moreover, it is possible to write an arbitrary symmetric polynomial as a polynomial of these sigmas only once in a unique way. The proof, a proof for this result will come in the next video. See you soon.